So in this video, we're going to go over a couple of examples to show you how the z-test works when we're comparing the proportions of two different groups. Remember that the z-statistic for this test is calculated as the sample difference, so this is the difference between our two groups when we sample each of the two groups, minus the hypothesized value. So the hypothesized value of the difference between the two groups is 0 because oftentimes we're assuming there's no difference between the two groups, so we'll just subtract off 0. Because we're assuming the two groups are the same, we're going to use the pooled standard error to get our measure of variation. So this is the standard error, and it's calculated using that pooled proportion, but it also accounts for the fact that we're sampling perhaps two different groups and that have two different sample sizes. So we want to take into consideration N1 and N2. Those are the two different sample sizes that we've looked at. So the steps that we're going to go through to calculate that test statistic are first to find that sample difference. So we need to, in our word problem, figure out what our two samples are and which one we need to put first. Oftentimes in these problems, we'll put the larger group or larger proportion first and the smaller one second. That way, if we have a difference, it's always going to be positive. But really, it doesn't matter which one you put first. It's only going to change your interpretation at the end. So it won't change your conclusion. It will just change your interpretation. So make sure you make note of which proportion you're putting first, and if the question asks you to put a particular group first. Calculate the pooled proportion, so you're going to put together these two proportions, and I showed you that in the previous video, so that we can calculate that pooled standard error. Once we have those three components, we can determine the alternative hypothesis, and the alternative hypothesis is going to be based on whether or not we think one group is greater than the other group. Once we have that alternative hypothesis, we can calculate the z-score when we assume no difference. Again, that assumption of no difference is the reason why we subtract off 0 from the top. And then once we have that z-score and the alternative hypothesis, we can calculate a p-value from the z-score. So here's a problem where we're looking at two groups. We're looking at white women and black women, and we're looking at the rate at which they have multiple births. So you can see that the sample size is different for white women. They've sampled more white women, and because of that, more white women had multiple births. For black women, there's fewer of them, which is why we see fewer multiple births. So we don't want to compare just the overall number of multiple births. We want to compare the rate at which these two types of women have multiple births. So here I've calculated the rate at which white women have multiple births, that's 0.0266, and the rate at which black women have multiple births, that's slightly higher at 0.032. Now you can see that black women's rate is higher than white women, but we want to know, is this difference statistically significant, or perhaps the reason why this black women's is higher is just because of sampling variation. We know that some samples are higher and some samples are lower, so we want to know, is this statistically higher or is it just due to that sampling variation? The next step is to calculate that pooled proportion, where we assume that the two groups are the same, and so we compile all of the successes, which is the total number of multiple births, and divide by the total number of people that we sampled, both black women and white women. When we calculate that, we get a pooled proportion of 0.0275. We can use that pooled proportion when we calculate our standard error. So our standard error is just the square root of 0.0275 times 1 minus 0.0275, which is how I got 0.9725. So that's just the Q, 1 minus P. And then I'm going to times those by accounting for the sample size. So 1 over the sample of white women plus 1 over the sample of black women. And this is how your book does it. I did it slightly different in the last video, but both of the methods are correct algebraically. And so you're going to want to do the division first, then add up, and then do the multiplication, square root last, and that will give you a standard error of 0.0072. The next step is to determine the null and alternative hypothesis. Remember that we always put equality in that null hypothesis. So here we're saying that the difference between white women and black women is equal to 0. So we're saying that the two groups' proportions are the same. The alternative hypothesis is just that they're not equal. We're not saying that one group is greater than the other group, just that based on our sample, we indicate that there is a difference between the two groups. We can examine that sample difference using the z-score then. So we're going to calculate the z-score by calculating the sample difference. Here I put white women first, but again, it doesn't matter which group you put first. All that's going to affect then is how you calculate your p-value. So here we put white women first, then black women, and that's going to give us a negative z-score. If we put black women first, we would get a positive z-score, and so we would calculate the p-value slightly differently. So once we have that, we can go on and calculate our p-value. So here, the p-value is calculated based on how we've defined the alternative hypothesis. Since we said that we want a difference that's not equal to 0, the z-score that we're looking at, we compare to what we calculated, and we're looking at the fact that they're not equal. The way that we calculate this probability then is we want to look at everything less than negative 0.75 and everything greater than 0.75. This is mostly because we are dealing with an absolute value. What I've shown you before is that you can just take that probability and times it by 2. So because we are dealing with a negative z-score, you'll reach below and times by 2, and that gives you 0.4532. But an equivalent statement would just be to reach below negative 0.75 and reach above 0.75, the positive value. These probabilities are going to be equal because of the symmetry of the normal model. So our conclusion is based on this probability and the significance level that was given to us in the problem. Here we find that our p-value that we calculated is greater than our alpha level. So we have to fail to reject the null hypothesis. We just don't have enough evidence that there is a difference between these two groups. Our sample shows that there is a difference, but there's not enough spread between these two to indicate that there is a strong difference. It's not an unusually large difference. And so the difference that we do see may just be because of that sampling variation. So that problem had an alternative hypothesis that was a two-tailed test. Let's now look at a problem that the statement asks us to generate a one-tailed test. So in this problem, we're looking at a study of whether regular mammograms helped prevent deaths from breast cancer. We surveyed women who had never had a mammogram, and we surveyed 30,761. Only 197 actually died of breast cancer. For women who had mammograms, we surveyed slightly fewer of them at 30,360, and only 162 of them died of breast cancer. So you can see fewer total number of women died of breast cancer, but we also surveyed slightly fewer women who had mammograms. And so we want to make sure that we're looking at the rate and not just looking at the level, because the level is an incorrect measure. So the first thing we want to do is we want to generate our sample proportions. So we are given the proportion of women who died of breast cancer that didn't have a mammogram. You can see that's slightly higher than the proportion of women who died of breast cancer that did have a mammogram, which is 0.0053. When we pool those two together, we're assuming that the true rates of death from breast cancer are the same for both groups of women, those who have had a mammogram and those who have not had a mammogram. And that pooled proportion is 0.00587. We're going to use this pooled proportion to generate our standard error. Again, that's just the square root of that pooled proportion times 1 minus the pooled proportion. That's how I got 0.99413 is 1 minus 0.00587. Then we want to account for the sample size, so we're going to do 1 over the sample of women who had never had mammograms plus 1 over the sample of women who have had mammograms. So this is actually, because these two numbers are so large, we're going to end up with a really, really tiny standard error, and you can see that it's 0.00062. That's a reasonable standard error given that our sample sizes are so large. And this is why we want to sample as much as possible, or more data is always better, is because a larger sample size means that you have a smaller standard error, and so you can be more precise in your estimates. So the next step is to determine our null and alternative hypothesis. Again, we put the equality in the null hypothesis, and so we're assuming that the true difference is 0. So we're assuming that the two groups of women are the same. The alternative hypothesis then indicates some direction. So here we want to know, do these results suggest that mammograms have a lower rate of breast cancer deaths? So here, to have a smaller rate with mammograms means that this proportion is going to be smaller than the rate for women who have no mammogram. If P no is greater than P mammo, then this total difference has to be a positive term. And so that's how we get this greater than sign. So that difference has to be greater than 0. And we're going to use that when we calculate our p-value. The next step is to calculate our z-score. We put first our sample difference, and because in the hypothesis we put no first, p no first, that's what we're going to put first here. And then we're going to put second p mammo, because that, again, we want to be consistent with what we put in the alternative hypothesis. We subtract off 0 because that's our hypothesized value, and then we divide by the standard error. So that gives us a z-score of 1.772. So now we want to calculate our p-value, and our p-value is just the probability that we observe the sample we do or something greater, and this probability is generated from that alternative hypothesis. Our sample gives us our z-score, and so the equivalent statement to that is that we see a z-score that we do or something greater than it. Again, the direction of these two signs are always going to be the same, and they're based on how we specified that alternative hypothesis. We can then use our z-tables to find this probability. Remember, the z-tables give you everything that's below, so you'll have to do 1 minus what you find in the z-table, and that's going to be 0.0379. So with this p-value, we can see that it's greater than our alpha level, and our conclusion in this instance is that we again failed to reject that null hypothesis. We do not have enough evidence to suggest a difference between these two groups of women. Now, this is largely because we predetermined that significance level, saying that we are requiring a very, very large level of evidence. And so that's going to make your alpha have to be really small. You can see that the p-value is actually quite small, but because we're requiring so much evidence, our level of requirement, remember that's like beyond a reasonable doubt, is actually really quite high. Here, the magnitude of the number is low, but the level of evidence is very high. And so that's why we fail to reject, is because we are requiring a large amount of evidence, and we do have some amount of evidence, just not a strong enough amount of evidence to suggest that there is a difference between these two groups. So that's a few problems, and these are the steps that I went through to answer some of those questions to compare two proportions. We can also use confidence intervals to test two proportions and to see if there's a difference between the two groups. And I'll show you in the next set of videos how to use a confidence interval for the true difference to generate a hypothesis test.